what is this shape? It's a sphere. Okay? So how do we describe a sphere?
Round.
Round, it's kind of circular. So if it's round, if it's circular, what constant are we going to have as part of our calculations? Pi. So pi is going to appear in this when we're trying to figure out surface area and volume. What would be the surface area? What would it mean to calculate the surface area of this orange? The peel. So if I could take the peel off and figure out how much space it took, I could figure out its surface area. That's what you're going to do. So the first thing that I'm going to have you do is try to make sure if your orange seems a little bit oblongy, if you have to, roll it around on your table to make it more circular. Don't squish it because you do have the chance to eat the orange afterwards. Once you've done that, what are these?
What are those measuring things?
Caliper.
Calipers. So we can use the caliper to measure what? Diameter. So you're going to measure the diameter of your orange, but we're not going to take the measurement once because in science class, do you ever do an experiment once?
Yes.
Yeah.
Seriously? Sometimes?
I'm lazy.
If it hurts.
If it hurts. Should we do the experiment just once?
No.
No. You're going to take 3 measurements of your orange in 3 separate areas, and you're going to write it down. So I am going to bring you a piece of paper to do that. Once you have your diameter, you're going to average them. So how do you average 3 numbers?
Add them, divide by 3.
There we go. Okay, so that's your first start. So, what have you done so far? What have we done?
We measured oranges.
What did you measure on the orange?
The diameter.
The diameter, and then what did we do with the diameter?
Found the radius and drew some circles.
How many circles do most of you have on your page?
6.
Okay. And what did we say we could do to find the surface area of my orange? What did the surface area correspond to? The peel. So this is what you're going to do now.
Peel orange.
Peel the orange, and as carefully and as accurately as possible, fill up the circles. So do you want big pieces of peel or small pieces of peel?
Big.
You might want some big, but you might need some small because you're going to try to cover that area, and you want to be as accurate as possible. So you want to leave as little green space as possible on those circles that you drew.
Okay, pass it along, You have fingernail.
Phones away, guys.
Yeah.
Peeling oranges. Because I want demonstration. I want evidence of student achievement.
We have an achievement here.
Do you have achievement there? Maybe, maybe not.
Before someone dies on camera,
Who's going to die on camera?
call it.
Yeah, I can peel it now.
So how many oranges are you filling up?
I got like 3.
You got 3?
4 probably. I
4?
think we're gonna get 5.
Do you have a lot of green space on some of your oranges though?
Yeah.
So maybe fill up some of the green space that you have?
Yeah.
So how come you guys flipped your orange peels upside down?
What?
How come you have some of your orange peel flipped upside down?
So it can go, I don't know, just because we like it like that.
Does it fit better?
Sometimes.
Sometimes? How many oranges are you filling up?
4
Or circles,
so
I guess.
far.
4? What do you guys have?
4-ish.
4-ish?
Well, these ones were deformed, kind of. Our orange was deformed as a...
What if your pieces of peel were smaller? Would that make a difference?
No.
Probably not.
Probably not? I think it would.
It would, but I'm too lazy to do it.
So how are we doing over here, guys?
Good.
Getting there?
Yeah, trying to fill up all these
Trying to
other
fill up?
spaces.
Do you think you're going to have to use all 6 circles?
Probably not.
Probably not. So maybe try to use as few circles as possible. How are you guys doing? Good. Getting there? Yeah. Good. It's like the giggly group over here. So how many circles are we getting?
4 and I don't know.
4. But do I have quite a bit of green space? I see quite a bit of green space on some of your circles. Can we squish that up a bit more? Okay, so can we come up with some general consensus as to how many circles you were filling up with your orange peel?
4.5.
4.5? What did you guys get on the back? Paula? 4 and a little bit. Connor? 4. Eric, how many did you guys get? It looks like you have a lot of green space on your oranges. Do you think that if you squished up your green space, you'd have less than what you have there?
Yeah.
Samantha, how many circles did you guys fill?
4.
Isa, how many did you guys fill?
4.
Kate?
I think it's like 4.5.
4.5? What happens if I go like this? How much more space I just opened up, right? So if we kept our orange peel sizes much, much smaller, all this space right here, do you think maybe eventually, like if I took this part out, that's not what it's okay,
No, you're not.
you see what I mean? So how many circles do you think I could fill up? 4. So what is the area of each circle? What is the area of a circle?
Pi r squared.
Pi r squared. So my sphere, so the surface area of my sphere was 4 circles. Ta-da! There's the surface area of a sphere, ladies and gentlemen. No clapping? You will remember this a year from now, I guarantee. I asked the grade 11s this morning. All we had to do was start talking about the orange activity, and they were able to connect that, yeah, it was 4 circles that we filled up. So now we're going to look at volume.
Yay.
So for volume, so now that we've looked at the surface area of the sphere, we're going to look at the volume. So volume can be interchanged with the amount of space it takes up, or it can be looked at as capacity, the amount of space that it holds. What do I have here? What do I have here? What do you notice? Fits in. So it has the same diameter and it has the same height. So it's kind of like the demonstration I did with the cone and the cylinder, the pyramid and the prism. So there was a relationship between the 2 measurements. So the question is, does a similar relationship exist between a cylinder and a sphere? What do I have? I have a sphere filled with water.
Oh, you got,
So
you got
I've got
green Kool-Aid
capacity.
today.
I got green Kool-Aid today. I probably wouldn't drink it.
You made a pot.
Yeah, I know what I'm gonna do. It's fun. There's a boundary. I haven't did it yet.
That's fine.
No problem, hold the pot.
Yeah, you have.
More or less than the cylinder?
More.
The volume of the sphere, is it more or less than the cylinder?
Less.
Less? How much less?
What about a third?
About a third? How can we figure out whether or not it is actually a third?
calculate the height and then
What's the cone in comparison to the cylinder?
3 cones equals 1.
3 cones. So if this is about a third remaining, how many cones should this be?
2.
1.
Be 2?
Ah, got you all. Got you all.
You should have seen last time.
What happened last time?
There was a lot messier.
That's why she has the bucket now.
That's why I have the bucket that got spilt and the water that got spilt. With the water that I think I have laying on the desk, how many cones did I fill? 2. So I have that the sphere,
It's 2/3 of the cylinder.
2/3 of the cylinder, okay. So a sphere, so the volume of a sphere ends up being 2/3 the volume of a cylinder. What is the volume of a cylinder? How do I find the volume of a cylinder? Oh, that's surface area.
pi r squared 8.
Pi r squared 8. It's the area of the base times the height. So the area of the base, which was pi r squared times h. The problem with this is if I'm looking at a sphere, so if I'm looking at a sphere, there's no height to a sphere. What I have for a sphere is its diameter or its radius.
That could be the height still.
So what could be the height?
The diameter.
The diameter. So the diameter could be the height. But you know what? I don't want to have D's and H's. I want to have only one letter. So how could I use the letter R?
You could just cube it.
Cube it. How many R's in one diameter?
2.
2. So now if I put that into my formula, I have R squared and then I have 2 of those R's. Now we get what you were saying, Brianne, with cubing. So there's my R cubed. And then if I take 2 and I 2/3 and I multiply it by 2. So what are 2 groups of 2/3? 4/3. And there is the formula for the volume of my sphere. Which totally got missed on the screen. There we go.
Let's do it again.
So if we look in the workbook now at the surface area and the volume of spheres, the first part just talks about what Gary used, the method of displacement to determine the volume of a sphere. So displacement would have actually been, I'll show you what displacement looks like. Displacement is if I fill the cylinder up with water. Oh, nice pretty green color for St. Patrick's Day.
You did that on purpose.
No.
Can't pull one over on you. Displacement is what Archimedes, it's the principle of Archimedes when he jumped into the bathtub and went eureka.
Isn't it the weight of the object is how much water it takes?
Still the displacement.
It's the volume.
Yeah, the weight.
There's my displacement. 1 cone. So there's the other way of 2/3. So in Gary's example, he used displacement to show the relationship between the volume of a sphere and the volume of a cylinder. By going back to mass is a measurement for volume, mass is also then connected to capacity. So on this part of the page, this is where Gary's looking at the volume of his sphere. The first question asks mark the radius of the sphere and the cylinder on the diagram and explain why the height of the cylinder would be 10 centimeters. Well, the radius of the sphere is 5. So if the radius is 5, the diameter becomes 10, which corresponds to the height. And then using that displacement, that 2/3 the volume of the cylinder, he gets 2/3 of 5 squared, pi r squared, times the height, which he has at 10. And then this becomes 5 cubed, because this would have been better if I would have left it like that. Then I've got 5 and 5 squared is 5 cubed, times pi times the 4/3. If you do that calculation on your calculator, what do you get to the nearest tenth of a unit? Does it start with a 5? Next number?
2.
Decimal. And what are my units used? And because I'm calculating volume, it would be centimeters cubed. And if you notice, it's the 5 centimeters that's multiplied by itself 3 times. 5 centimeters times 5 centimeters times 5 centimeters. There's my centimeters cubed. And then in the next portion, what Gary did is instead of looking at it as a height of 5 centimeters, he looks at it in terms of r for the radius and the height being 2r. And that's how we get our formula of 4/3 pi r cubed. So the next page looks at the 2 formulas, giving you the 2 formulas. The actual proof for the sphere, the surface area of a sphere, involves calculus, which is out of the range of what we do in math class. It would be covered, I believe it's covered in Math 31. And it's the same as the surface area of the cone. The next part just talks about hemispheres and understanding the terminology behind a hemisphere. A hemisphere is half of a sphere. So if I was to determine the surface area of a hemisphere, so if we were looking at the surface area, or actually let's look at the volume. The volume of a hemisphere. Take the volume of a sphere, which was 4/3 pi r cubed, and divide it by half. In terms of division by a fraction, how do I divide fractions? Reciprocal. So I multiply by the reciprocal. Oh, that's not divided by 1/2. It's divided by 2. There we go. Which then would become multiplied by 1/2. If I take 4/3 and I multiply it by 1/2, what would I get? So 4/3 times 1/2. 4/6, which becomes
2/3.
So I would get 2/3 pi r cubed. That's the volume of a hemisphere. 2/3 pi r cubed. Now if I think of the surface area of a hemisphere, in the surface area of a hemisphere I have this curved portion. That curved portion is half of the curved portion that I have with the whole sphere. So I have 4 pi r divided by 2. And what is 4 pi r squared divided by 2? 2 pi r squared. And then I have this circular base. And that circular base is the area of another circle, which together gives me 3 pi r squared. If I did not have that circular base and I just have the curved part, it would only be 2 pi r squared. Unless otherwise stated, you will always assume that the base is included in a hemisphere. Unless you're specifically told otherwise. So let's look at the 4 examples that we have. The shape of the planet Pluto, which is now still a planet, is approximately that of a sphere with a diameter of about 2,302 kilometers. What I would like you to do, and I'll give you a couple of minutes, is calculate the volume and the surface area of Pluto. And answer to scientific notation, because you're going to get large numbers here. So if I put these calculations in, for the surface area, I've got surface area equals 4 pi r squared. And half of the diameter ends up being 1,151 kilometers. So for scientific notation, .7 times 10 to the 7th square kilometers? Yes or no? Okay. Did your calculator automatically put it in scientific notation for you? No? Okay. Good. You should be able to do that yourself. Calculate the volume. 4/3 pi r cubed. So that cubed button on your calculator, that's the little button that has, it's kind of the arrow up or the little pat. That means power up. And what do you get this time? Good job, thank you, Isa. 6.4 times 10 to the power of 9 cubic kilometers. So think of how big a cubic kilometer would be, because it's 1 kilometer by 1 kilometer by 1 kilometer in height. And I have times 10 to the power of 9. So that's hundreds, thousands, millions. That's 6.4 billion cubic kilometers. And Pluto is one of the smallest planets. Candy used a rope to wrap the outer edge of a beach ball once. So if Candy uses a rope to wrap the outer edge of a beach ball, what is she calculating on the beach ball? The circumference. So Candy calculated the circumference of the beach ball. Then she took the rope and laid it out straight and figured out the distance was 108 centimeters. So their circumference, which equals pi times diameter, their circumference is 108. So what's the diameter?
34.4.
Exactly 34.4?
No.
34 point what?
3774677.
Okay. And then I need to determine the volume. Being 4/3 pi r cubed. What do I have to do with that 34.37 da 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 da?
Divide by 2.
Divide it by 2. So that would give me right radius.
17.1887.
And that's the number that I can bring into this formula. we want to do our best to make sure that that formula or those numbers are kept as whole as possible, or as true as possible. So we start off with 108 divided by pi. That gave me my diameter. I divided it by 2, and that gave me my radius. If I now raise it to the power of 3, notice what comes up. ANS, which stands for answer. The previous answer to the power of 3 times pi, oops,
2, 1, 2, 7, 2, 1.
there we go, times 4/3. So I can go 4 divided by 3 in brackets to write in my fraction of 4/3. 21,272
Yeah.
to the nearest tenth of a centimeter. So this would be 0.6. Okay? So 21272.6 cubic centimeters. Good job. Dana and Don are constructing dome tents in the shape of hemispheres. Dana's tent has a diameter of 4 pi and will have the base made as the same material as the dome. Don's tent also has a diameter of 4 pi, but he has chosen to not construct a base for the tent. Calculate in terms of pi how much material Dana needs to make her tent. So what am I calculating? Volume or surface area? Surface area, and it's of my hemisphere. So if I include the base from the previous page, what is the surface area of a hemisphere with the base? 3 pi r squared. And in our formula, r, what is r equal to? So the diameter equals 4 pi. The radius would be half of that, 2 pi. So 2 pi squared. So if I square 2 pi from my exponents chapter, square 2 and it becomes 4. And when I square pi, it will just become pi squared. 4 times 3. And if I take pi and I multiply it by pi squared, pi to the power of 3, or pi cubed. And this would be, it doesn't give me units. It just says that the diameter is 4 pi. So then I would write down units cubed. Because it could be kilometers cubed, it could be centimeters cubed, it could be millimeters cubed, it could be feet cubed. I'm not told what 4 pi measurement is. Don doesn't have a base to his tent. So when he calculates his surface area, what will his formula look like?
2 pi.
So I get 2 times pi times 2 pi squared, which is still 4 pi squared. This time 2 times 4, 8. And I get 8 pi cubed. Units, sorry, that should be units squared, right?
Yeah, I was just gonna say that actually.
Thank you, Jonathan. Class example number 5, we have to work backwards. The volume of a basketball is 433.5 cubic inches. Determine the radius. So what should I start off with? What am I calculating? What am I given? So I need my volume formula. Now fill in what do I know. So I know the volume, 433.5. And what's my goal? Figure out the radius. I want to get r by itself. So to get r by itself, I first of all need to get rid of 4/3. Multiply by 3/4. Because when I multiply by the reciprocal, I get 12 over 12, which equals 1. Okay? So I multiply by 3/4. So that's going to leave me with pi r cubed. How do I get rid of the pi? And then cube root it. So my final answer would be the cubed root of 3 times 433.5 divided by 4 pi. So I could put this into my calculator a couple of ways. I could do this step by step, which we might find the easiest way. So I take 433.5 and I multiply it by 3/4, which I don't even need to write as a fraction because I know it's 0.75 as a decimal. Then I divide that by pi. Then I have to cube root that answer. So to find the cube root on your calculator, you press the math button, and it's choice number 4. But I'm lazy. I don't want to have to type this whole number in.
Second negative.
Because above the negative in blue is A and S. So anything that is in blue, I can activate by pressing the second button first. And what do I get? 4.694977. So to the nearest centimeter, how many centimeters is that?
5.
Is it?
It's 5 inches.
Thank you. So how do I convert 5 inches to centimeters? One inch is equivalent to, right, and I have 5 inches, so I'd multiply by 2.54. And actually, you know what, I don't even want to round this to 5. I want to leave this as my 4.69, because I only want to round my final answer. So if I grab my calculator out, multiply that by 2.54, and what do I get to the nearest centimeter? 12, so I've got 11.92. So I get 12 centimeters. You have to read the question carefully. So questions 1A and B, 2, I probably don't need to give you 6, 7, 8, and 9. I could probably pick just a couple of those ones. Oh, I like question number 6 though. Number 8. And 14.